In this lecture, I want to do an example that follows from the paper that I've been so excited about in the last few lectures in this General Relativity course. That was this paper here. We've already really exploited the heck out of it. We're not done exploiting it all because we haven't yet done the analysis of the Einstein tensor, which is coming up. But they have a really fun example that I think is worth working out, and it's on page 170, about page 170 of this paper, and it's about the pullback and a coordinate change. And so I want to kind of discuss this particular example because it illustrates this pullback concept, which we've already done, but you can always do it again, right? There's no harm in that. But it also shows the unlimited level of flexibility coordinate changes give us in general relativity. And it gives you a sense that these coordinate changes can actually be quite arbitrary and deep. So this example is actually quite simple, but we're going to just walk it through anyway as to sort of refresh these two ideas. So let's begin. So we need to quickly review the idea of a pullback of a cotangent field. And the way we set this up when I first taught it in this lecture series, which was, I think, lesson 57 and lesson 58, was we set up one manifold M, and which we called Marshall, and manifold N, which we called Neal, because M and N are so common manifold names, but M and N are difficult to distinguish with just a recording. So we call it Marshall and Neal. Not intending to be cute, but it's cute anyway. So the idea was, if you have, remember, a manifold is a set, right? And if you have two sets, you can have a mapping between the two sets. So this mapping between the two sets we called phi. So we're mapping Marshall, points of Marshall get mapped into points of Neal. And once that happens, once you have such a mapping phi, you're forced upon us to get, you're forced to deal with the push forwards and pullbacks of various things, including cotangent fields on Neal. So if I have a cotangent field on Neal, which I might call alpha of P, where P is a point in Neal, so P is an element of Neal, then I can take this cotangent field and I can pull the field back to create a cotangent field over here, which I think the notation was phi star. Let me check. Yeah, that was one of the notations I used. So this is phi upper star alpha of x. You know, I wrote the star like an asterisk, which confuses a lot of people because it looks like some sort of conjugation. So let me change that to a no kidding star. And the idea is that this object, phi star acting on alpha, this is a cotangent field in Marshall. So as such, you might think of it as a cotangent field that acts on x, where x is an element of Marshall. So the point from lessons 57 and 58 was, if you have a function that connects these two manifolds, you automatically have a function that will take cotangent fields on Neal. Now remember, it's a whole field. So this alpha acts on every point at Neal, and it returns a cotangent vector at every point in each cotangent space on Neal, and it returns an object over here, which is a cotangent field on Marshall. And that's the general idea that we explained in great detail. I think in lesson 58 we explained that. Yes, it was lesson 58 that we explained this in detail. So now we're going to actually use it again. We used it, of course, to understand the scalar curvature at the time. We presented it the first time. Now we're going to use it to understand something slightly different. All right, so then what we reminded ourselves is that, okay, this is good in general terms, in coordinate-free terms, but if we actually go ahead and throw down charts on Marshall, and when I say the word throw down charts, actually I should say choose charts to be a little bit more academic, right? If we choose charts on Marshall and on Neal, that's just saying we establish a coordinate system. Frequently you'll see in the literature, if we choose charts or select a chart or fix charts, That's just saying now we've got a coordinate system, because once we say we choose charts, what we're basically saying is we've got little regions inside Marshall that have maybe overlaps, and each of those regions can be mapped homeomorphically to Rn, and those homeomorphic mappings are the chart mappings gamma, where I indexes each chart, or I guess I being up or down doesn't really matter, so gamma maybe I. It's not meant to be a space-time index, it's just a mapping for the ith chart region, right? This is UI, and that's the mapping for UI. All that stuff happens when you choose charts. So if we choose charts, we are establishing a coordinate system. So once I do that, I can now say, okay, every point in Marshall has coordinates x0, x1, ... to x n minus 1, where n is the dimensionality of Marshall. And that means that this mapping, of course, is a function of now the coordinates of the points, because we've established coordinates. So, but we've also got coordinates on Neal. So this takes this n-dimensional manifold here and the n dimensions, and it's putting it in Neal, which may have a different number of dimensions. I suppose we should change this a little bit. We should say this has little m minus 1. So Marshall, the dimension of Marshall is equal to little m, and the dimension of Neal equals little n. How about that? Little Neal. Anyway, so that's this here, this, when I say this, I should point, right? Let me erase this and try to draw it a little bit better. This is a little m minus 1. How about that? Okay. So now, but the point I'm trying to make here is that this function should give you the n-dimensional coordinate of a point in Neal. Given coordinates of a point in Marshall, it should give you the point in Neal. So this function has to return n different coordinates. So of course that means that there's really little n of these size, right? Little n, they take the coordinates of a point in Marshall, and they return the ith coordinate of the point in Neal. So you have n of these functions. So with that in mind, we can create this mapping as we did in lesson 58, I think it was. Yes, it was lesson 58. We can now construct this mapping of a covector field in Neal. Its pullback we can construct in Marshall. And I gave that formula in lesson 58, and I'm going to repeat it right now. And voila. What this tells us is that the pullback of the basis vector covector field, the basis covector field VI, presumably the coordinates in Neal are given by V mu, and the coordinates given in Marshall are given by X, say nu, right? So this is the X coordinate system, and this is the V coordinate system. So the pullback of a basis vector field, the coordinate basis vector field in Neal, is equal to this partial derivative summed into the basis vector field in Marshall. And this partial derivative is totally doable, right? Because if we have this function psi that goes from Marshall to Neal, and we've chosen charts, therefore we have I versions of psi, right, that are functions of the coordinates, and we can take derivatives of this because manifolds, right? It's all because of manifolds. Manifolds, the whole structure of manifolds is what makes this thing possible. So this derivative is a straight up partial derivative of regular calculus. This is a sum. And so we can pull back any basis covector field. So any actual vector field, well, basis vector fields are actual vector fields, but if we take an arbitrary covector field, it will be constructed in terms of its basis covector fields. We pull back each of the bases covector fields in linear fashion. Using this formula, we can then construct the covector field in Marshall. Okay, so we had to review that a little bit, because what we are going to do is we are going to take a manifold Marshall and a manifold Neal, and Neal is actually going to have a metric tensor. And we're going to pull back the metric tensor into Marshall. We did this exact same thing when we studied the scalar curvature. It was quite complicated then. This one will be much, much simpler, but it's not designed to study this. This is actually just a review. And for those of you who've been following this, I have no hesitation of excessive repetition and reviewing. It's just my thing, right? There's nobody hassling me to teach this thing in one academic quarter, right? So I'm going to take 2 years. I don't care. So reviewing this doesn't hurt. But so I've reviewed this whole concept so we can apply it for a case that's even simpler than the one we've already done. Okay, so with this review in mind, let's do our setup and study the more interesting thing that we wanted to study today. All right, so let's start with Marshall. I want Marshall to be S1. So the name of this manifold is actually S1. I'm going to give it the alternative name Marshall just because I want to make contact with this setup over here, all right? But this is S1. S1 is the circle. A circle is a manifold. It's known to be a manifold. The problem with this picture of the circle is I've clearly laid out this circle on a plane, right? I've laid it out in the plane. So when you're viewing this version of S1, you're already thinking about it embedded in the plane. But that embedding is sort of an artifact of our analogies and our thinking because and the way this has been presented to us, because S1 can also be considered as a straight line where these two final points here are identified. So the point at the left endpoint and the right endpoint are actually the same endpoint, right? And you consider it a set of all these points on the line where each point is an element of the set, but these last 2 points are kind of combined into like a mini set, and that set is thrown in there too. And everything that's inside here is of equal merit, including this thing. Even though each of these only represent 1 point, and this guy represents 2, it's thrown in the manifold as an equivalence class of points, basically. So this is a legitimate way of thinking about it. And then once you put charts on it and mappings to R1, because remember, this maps to R1. S1 maps homeomorphically to R1, or each chart of S1 maps homeomorphically to R1. So because of this, there is this inherent tendency to envision S1 as a circle, and there's a very, very good reason for it. But what we're going to do in this lecture is we're going to unpack this in a little bit more of an abstract fashion, and we're going to take S1 and actively embed it in the circle so that Marshall is going to be S1 and Neal is going to be R2, right? Neal is going to be R2. So let's set that up. So the first thing I'm going to do is I'm going to try to see if I can make some sense of this, right? I'm going to erase it as a circle. I'm going to sort of draw it more like as a straight line where these 2 points are identified, right? They're identified. So if you're traveling along this line and you're here, and you move here, and then all of a sudden you're at this point, well, you're also at this point instantly. So you can't be at just this point. You've got to be at both endpoints at the same time, right? Very abstract, and of course, if you think about it in terms of a plane, you've got the problem, well, you're not at the same location, but you are because this is not in the plane. This is some abstract thing that's out there. And in fact, how do we know where we are along this line, right? Well, what we're going to do is we're going to choose charts. So we're going to give a coordinate system on this thing. We're going to call it theta. And every point is going to have a value of theta. So that's the theta, that's point P. It's going to have theta of P. If this is point R, it's going to have theta of R. And of course, we can do this because it is just one big manifold. So there is our S1. Now we're going to map this thing using the transfer function phi. I was calling this at the end of those lessons 57 and 50. I was calling this the transfer function. which I felt really awkward because I spent a lot of time studying automatic control theory, and the transfer function has a lot to do with Laplace transforms and things. So this isn't really that, right? This is, but I like the language. So this is the transfer function. You're transferring Marshall into Neal, right? So there, we are going to invent a transfer function now. So that transfer function we're going to call, psi, and it's going to take, we've already got coordinates, so it's going to take the coordinates of a point in S1, and it's going to deliver something in R2. And what is it going to deliver in R2? That's a very good question. And that's where this paper kind of starts. Let us say, for the sake of definiteness, that phi, this first point we'll call, let's actually put the point P at the very beginning, right? So this point at the beginning, let me blow this up. This point at the beginning is the point P. And we will write theta of P equals 0. So we're going to say the coordinates in Marshall, in the S1 manifold of point P is 0. And as you move along, the coordinate changes, and it increases to some positive value. Then when you get to the end, it has some positive value here at, say, point Q. We'll call that point Q. And theta of Q, we'll call that some number. I want to give it a number. Let's call it some number A, right? It has a value A. So the coordinates of the point with the coordinate 0 and the point with the coordinate A, those are identified. Those are the same point, right? So now we might consider a mapping from Marshall into R2. We're going to now map everything into R2, which is Neal, right? And we have to choose this mapping. So here's a logical choice. So this choice here, where the first coordinate in Neal and the second coordinate in Marshall, I guess the coordinates over on Neal, the coordinate system on Neal is going to be x0, x1, like that, right? And I choose some constant r, right? Whatever, that constant could be anything. And then I take the cosine of theta over a, where a is this max value. So theta over a becomes 1 as theta moves over to q, and then multiply it by 2 pi. And then if I use this system and I set r equal to 1, say, just the number 1, because it doesn't really matter. I set r equals to 1, I'm going to end up with a circle. And this is the circle that we started with kind of over here. Well, the initial circle that we considered for S1. Now all of a sudden the embedding is done. So that embedding, that whole idea of considering S1 as a circle on the plane, that already involves this entire architecture right here. This entire architecture right here. So you might ask, you might say, well, okay, can you choose anything else? I mean, is there any other possible choice? And that's what this paper kind of talks about. It's like, yeah, of course there's other choices. There's an infinite number of other choices. And they provide an example of another choice. But before we show that example, we're going to simplify things a little bit, right? We're going to say, all right, let's, for this, I put this A in for the sake of argument, showing that, you don't really need to have this coordinate system laid out in any special way. But wouldn't it be nice if this just moved evenly along and it landed at 2 pi, so the coordinates of this point was 0 and the coordinates of this point was 2 pi? Wouldn't that be nice? Or no, I'm sorry, the coordinates of this point was 0 and the coordinates of this point was 2 pi. So if that's the case, then we can erase all of this stuff and we'd just go with, let's see, what would I do? How would I do it? I would probably go r cosine, r sine of just theta, right? And then you get a circle. But this form only depends on a very critical choice of how theta is laid out over here, right? Okay, so you end up with that transfer function. What other transfer functions might we choose? Well, here's a good one. You just put a 2 up front, right? And if you put a 2 up front, then this mapping will suddenly look like an ellipse. There's an ellipse, right? So you could do this either way, and nothing really matters much. I mean, well, there are two different mappings, so you end up with two different collections of points in R2 that represent all the points of S1. The first one is the one we kind of use all the time because why make things more complicated than they need to be? But then again, how much more complicated is this really? Okay, so that is sort of the meat and potatoes of this, because we are going to now presume that R2 has a metric, right? It has a metric. And for the purposes of this lesson, that metric is going to just be the standard Euclidean metric. And so here I've reconstructed everything so it's consistent with this picture here that we had with Marshall Neal. And I've highlighted these functions right here, right? So here's our abstract transfer function. This is the first coordinate of the transfer, or the first, I want to call it components, but we can't really say components because we want to leave that to refer to vector spaces and the basis of vector spaces. So the first of the n functions, because remember this over here is R2, so we expect there need to be two of these guys, right? Well, here's the first one, and here's the second one. And then I wrote down this to remind us how to calculate the appropriate metric, the appropriate basis vectors for covector fields over here. In other words, if we have a covector field in R2, I can pull it back using the pullback into S1, right? And now I'm assuming, so once you've assumed, I guess the way to think about this is over here we have a metric, and that metric is Gij equals delta Ij, and then it will be dxi tensor product dxj, right? So this is a covector field. It's a very simple covector field. It is the covector field of the coordinate basis, and this is a covector field. So we can pull back each of these covector fields to S1, right? We can pull back these two covector fields into S1, and thereby creating the metric on S1. So if distances in R2 are calculated using this metric, then distances in S1 will be calculated by using the pullback of this metric. Now that's not mandatory, right? Just because you have a transfer function and this space has a metric doesn't mean that you have to define the metric on S1 with the pullback. It does mean that you can create a metric on S1, which is the pullback of R2. Because remember, once you have this, you're forced to accept the pullback as something that can be done. But we're now going to say, well, if we're going to all the trouble of embedding S1 into R2, now I want to understand, well, I can measure, the distances along the circle using this additional fact about R2, which is this metric. I should be able to calculate what are the distances in this system using just theta. Simply, all I want is theta. Right here, I need to know, I need to know basically x0 and y0. Remember, this was x0 and this was x1, not y0, x1. So I want to be able to calculate distances just using theta. So I could take the pullback of this metric into S1 and then use that. And that's what we're going to demonstrate real quick. Well, the way that we do it is we do this formula, right? So the way this formula is going to execute itself is I want to say that the pullback of dxi equals the partial derivative of phi, let's see, dxi. Let's say the pullback, I need to do this one by one, right? So the pullback of dx0 is d phi 0, the partial derivative of phi 0 with respect to x0 times, hold on. Yeah, that makes no sense, right? Remember, phi 0 is a function of the coordinates in S1, right? Phi 0 is a function of theta. So it is just as a function of theta, and then times d theta. Now notice there's only one dimension in S1. So there's only one possible derivative to take here. So this sum that's indicated by this Einstein sum, there's only one term, right? That's that term. And then I repeat this process for the pullback of dx1, which is partial phi 1 partial theta d theta. And of course, partial phi 1 or partial phi 0 by theta is going to simply be minus r sine theta, and this one will be r cosine theta. And then this is d theta d theta. So now Gij, this metric's pullback, this is, by the way, I've just chosen a Euclidean metric, right? The fact that the metric on R2 is the Euclidean metric, which is represented by this delta function, is what makes it Euclidean metric. That was an arbitrary choice on R2. I could have chosen some kind of weird Lorentzian metric or any metric, but we're going to try to make this like normal geometry, so we're going to use the Euclidean metric on R2. And so now if I want the pullback of, so now I want the pullback of Gij, which, remember, this is a metric tensor field. These are tensor fields. This is a metric tensor field, so I can pull back covector fields, which is what they are, and that is simply going to be the tensor product of the new forms, right? If the pullback of dx0 is given by this and the pullback of dx1 is given by this, then the pullback of this means I substitute each of these with their pullback, and that's what this term is. And then I can write that as, okay, wait a minute, see, here's an easy mistake to make, right? I've got to blow this up. This is an Einstein sum too, right? So this is incorrect. I haven't blown up the Einstein sum. So let me do that first. First of all, let me erase this. It's close, but I just substituted it in too literally, and I forgot about the Einstein sum. So let me do that. Okay, that's more like it, right? So the pullback of this is literally the pullback. This here is what that is, right? I've blown up the Einstein sum using this delta function, and you end up with this dx0 tensor product dx0, dx1 tensor product dx1, and now I can make these substitutions for the pullbacks of each of these, because this pullback just goes right through it. You pull this back, you pull this back, you pull this back, you pull this back, and you get the pullback of the whole thing. And so if I do that, then what do I get? Okay, so the first thing is I get this, where I now make these literal substitutions. I put brackets so I could capture this sort of minus sign in here. So it's minus r sine theta d theta, tensor product, minus r sine theta d theta, r cosine theta, and r cosine theta. Of course, everything's linear, and we can pull out these real numbers. And what do we get when we do that? Now we multiply this stuff together. We get r squared sine squared theta, r squared cosine squared theta, and then well, that doesn't look right either. Yes, because these are now all, see, I forgot the key part, right, is this becomes theta, right? And now I distribute out the d theta tensor product d theta, and you end up, and of course the sine squared and the cosine squared combine to 1, and you end up with simply r squared d theta tensor product d theta, right? So the pullback, of Gij, this is in R2, right, is this thing, and that's in S1. So this thing, g theta theta, in S1 can be used as a metric to define distances between two nearby points in S1 or along whole paths if you integrate it. And just because S1 has one dimension doesn't mean it doesn't have it doesn't mean its metric is anything other than a rank 2 tensor, just like we've learned before. But now the paper very quickly goes from this to the idea that you have ds squared equals r squared d theta squared, which goes to ds equals r d theta. And that's certainly true, but because we're a little bit more comprehensive here, let's show exactly how and why that is. That is, let's make contact with the actual structure of how this thing works. And the way that goes down is, you have your S1 structure here, right, S1, and then you pick some point in S1, say P, and then you imagine a small, well, first of all, P is a point in a manifold. So ergo, it must have a tangent space, right? And the manifold is one dimension, so the tangent space will be one dimensional. And its coordinate basis will be partial, let me make this a little neater, partial theta. That'll be its basis vector. It's a one-dimensional space, has one basis vector. And this is the tangent space at the point P of S1. So if we talked about a small displacement along or through the manifold, we might describe it as a small vector at P that represents this displacement. And that vector will represent the change in the coordinates that you move, the small change in coordinates, and it's a vector, so it's d theta. So this is our displacement vector, a tiny displacement vector. So now I can take g theta theta. It's a rank 2, we would normally call it a rank 2 covariant tensor, but it's looking for a vector and another vector, right? And we are going to oblige by putting in this small displacement vector, which I'll go here. It's delta theta partial theta, delta theta partial theta. And that is going to equal literally this thing operating on these things. And by our literal definition, going all the way back to the beginning of our work in this course, that is going to be r theta delta theta squared, and then the dual space mapping d theta on partial theta multiplied by another instance of d theta on partial theta. And of course, these two things equal 1 by the definition of the dual space, or of the dual space mapping. And so now you end up with r theta delta theta. And that's what we tend to call ds theta. So ds theta equals r theta d theta. We now let delta theta, of course, become calculus sense infinitesimal. Remember, this is a one form, right? Now it's suddenly a calculus thing, right? And that's sort of the weird symbolism or symbology or notation things that kind of make this stuff really annoying, right? And then the small displacement ds equals r d theta, which is exactly what we would expect for the kind of mapping that we have invented, right? That is this mapping directly into a circle. Then I guess the last step would be just to integrate this. So you get, s equals the integral r d theta, the real finite distance, and of course r is a constant, so it becomes r, and then I guess you got to integrate from theta 0 to theta 1, so it's theta 1 minus theta 0, which is the difference, the finite difference in the angle theta, and in the coordinate value theta. So this is one way to do it. Now, when I say it's one way to do it, what I mean is this is one way to make this mapping. Now, you'll notice that, it's kind of abstract in the sense that theta along this line, right, it may not go out evenly, right? For example, from here it may be 0. And here, let's see, 2 pi is what? 6 point, say 2 pi is like, it's 6.28, right? So say it goes from here to here, and the value of theta only changes 1. And then from here to the q, now it changes the rest of the 5.28, right? So the coordinates that are laid out here, right, when mapped using this system, still give you this perfect circle. And the metric in this space still gives you distances in D2 that when brought back here, give you distances here that are kind of odd, right? Because most of the line is covered with very few coordinates, and a little bit of the line is covered with a lot of coordinates. And if you use this pullback metric, distances in this first part are short, right? Because you might go almost 90% of the line, but it's only, as far as this metric is concerned, the metric in D2 is concerned, that's still only about 1/6 of the total distance from P to Q. But that's fine, right? The distance is here on Marshall. That's all an artifact of the way our brain is looking at it, because again, I've plotted this as a line, right? But every point is just labeled with these coordinates, and this mapping and this pullback is what defines the distances. So now the question kind of is, okay, well, what if I used this system for the transfer function, right? With the 2 here, what happens in that case? So let's have a look at that. Okay, so here's the breakdown. We have our 2 transfer functions in coordinate form. We've got that new factor of 2 in there. That's really the only difference, right? The only difference is this factor of 2. And then I broke this down, didn't forget to blow it up this time. And I'm looking for the pullback of this metric. And that pullback is represented by these derivatives, right? And these derivatives are not very difficult to calculate. You take the derivative of this thing, you get minus sine 2r minus sine theta. And since there's 2 of them, I'm just bringing them out front together. And this one is going to be, oops, I have a little r squared in there, a little premature r squared. And that's r cosine theta. And you end up with this expression here. Now, there is a bit of a problem, right? In the paper, he uses the paper, I shouldn't say he, the paper's written by several people. But in the paper, they use this transfer function, but they land with a different expression. They actually land with this expression where the sine and the cosines are switched. But they definitely started with this expression. And if you look at these derivatives, I'm not quite sure. I think they just reversed them at the last second. So I guess what they actually did was they did sine and cosine ultimately when they did their calculation, but the transfer functions are written cosine and sine. I think it's just an error. So what I'm going to do in order to align ourselves with the paper is I'm going to work with this expression just so we can match the paper. So just take note that now in the middle of the calculation, we're just sort of switching this transfer function for no other reason than to be consistent with the paper, which is really, really good. So then using exactly the same logic as before, they end up with an expression that goes ds squared equals r squared 4 cosine squared plus sine squared, theta theta, and then it's d theta squared, right? So that they produce using exactly the same logic as we kind of exercised in this portion. They end up with this expression for this sort of squared little distance. Now, this makes perfect sense, right? If you look at this, you see that the differential distance when you use this transfer function for 2 different coordinate points on the circle as embedded in the plane is not going to be the same regardless of what coordinate you start at. In other words, if you go back here and we look at this, clearly if the way this is set up, these angles theta is this angle, right? That's how that transfer function was written. And here it's still true that this angle here is theta, but it's now true that for a given value of theta, a given change in theta, say this much, that distance is going to be very different than, say, this distance here, or this distance here, or this distance here. And in fact, the distance is going to be largest when theta is positions the location in R2 close to the vertical axis, or the horizontal axis, and less so other places. Do I have that right? Well, let's see. It would be the most, I guess, on this side, right? It'd be the most here because you're getting this full bendy arc, and here it's more like a straight line. So anyway, the point is it's not uniform for this embedding, and it is for that embedding. Okay, so we've done a lot of really good reviewing, and now we are in a position where we see that this embedding in two different ways has a very different effect on the pulled back metric on S1. In both cases, the metric on R2 is the same. It's the Euclidean metric, but the resulting pullback metric on Marshall is totally different, dependent on this function, this transfer function phi. The one that's the most natural, we like to think, is this one, but that's because we like the embedding so much, right? The embedding is what makes that natural, is this, we like this circle. And it leads to a very sort of systematic, distances along Marshall make a lot of sense. Although it still very much depends on the layout of theta, but without a metric on Marshall to begin with, the layout of theta doesn't really matter. I mean, with no metric, you really have no sense of geometry at all on S1. So you need a metric of some kind. So if you're going to embed it in R2, and R2 is a metric you're happy with, you might as well just pull it back to S1. There's really no harm in it. The point is that distances between points with different coordinates in S1, because S1 does have a coordinate system, and every point has a coordinate, and the distance between those points is now going to depend on the way you embed it into R2. Right? If you embed it in a very, very profound ellipse like that, you're going to have points that like this point here and this point here are going to be very far apart, even though their angular distance, theta, is the same. This distance here becomes very big, as opposed to, say, in this case, where theta, the delta theta is the same, but the distance is much smaller. So, you're going to, the embedding makes all the difference. So now we're going to have a look at how this embedding is affected by changing the coordinates on S1. We're going to do a coordinate change on S1, and then working with one of these embeddings, I guess we'll work with the intuitive embedding. We're going to see how changing the coordinates on S1 has a profound difference. And we're allowed to change the coordinates in a very arbitrary fashion, right? We can do arbitrary changes of coordinates, and we are going to choose a very exotic change. So the change I'm going to use is this one right here. It's kind of bizarre, right? The coordinate theta, this is the theta we know. This is the old coordinates, right? This is the old coordinates. Theta prime is the new coordinates. So I'm defining the old coordinates in terms of the new coordinates, which is, you have to be, we can do that. The new coordinates in terms of the old coordinates would be the process of inverting this, right? And inverting this is going to be very hard because I've chosen a very bizarre thing. I've chosen the elliptic integral of the second kind. It's a function. I guess I wouldn't call it a standard function. It's defined through an integral, or typically defined through an integral. And there's different ways of expressing this integral, but this is the way I want you to think about it, because this is the way that's most apropos for our lesson. But you'll notice that the new coordinate is in the upper limit of integration, and then we integrate this root of some number with 3/4, and you'll see that the square root of this is what appears as a parameter in defining the elliptic integral of the second kind. This 2 out in front is somewhat arbitrary, and this is how we express the old coordinates in terms of the new. So you'll notice that the way old in terms of the new, the reason I want to be able to do it is because we're going to transform the metric. We're going to take g theta theta, the metric, which is the metric on S1, right? This is the metric on S1 that was pulled back from R2, right? And we are going to convert it to g theta prime theta prime. We're going to convert it to the new coordinates. And the process of converting a tensor of any rank is you have to multiply it by the respective differentials of the coordinate transformation, or not differentials, derivatives of the coordinate transformation. And in this case, it's really, really simple because there's only one coordinate in S1. It's a one-dimensional space. So there's only one expression for the coordinate change, so there's only one derivative to take, right? So normally this would be written like this. Normally it would be written, you would write the transformation of the tensor components would be written in this way, where I prime and j prime are the new coordinate system, right? And ij is the old coordinate system. So these would be Einstein sums, right? So this would be a large complex sum over here. But if I and j can only run from 0 to 0, or from theta to theta, you end up with this expression right here. But, okay, so let's go with it, right? What is the derivative of theta with respect to theta prime? Now you'll notice I've set this up so theta is a function of theta prime, right? So this derivative is easy to take. Is it really that easy to take? Well, look at this weird function. I mean, what's the derivative of that? But, you know, it doesn't take too much recollection, but this is one of those weird things where easy calculus is so far away that it's hard to remember. But the fundamental theorem of calculus just tells us immediately that d theta prime by definition is going to equal this thing right here with phi replaced by theta prime, right? That's from the fundamental theorem of calculus. That is the something we learned so long ago that most of us have probably forgotten it, but it's very helpful in this case. And so I can write the answer like this. Notice I'm keeping the partial derivatives here, even though this is a function of one variable. Arguably it's a function of two variables, right? Because this parameter here, usually this parameter is described in the definition of E. This parameter here is k. Is it k squared or k? Hold on. It's just k. I think I've seen it as k squared somewhere before. Look out for this. I definitely, when I did this, I have the square root of k here, right? Because remember, I had 3/4 there. So it's pretty clear that I took the square root of 3/4 as the parameter, which implies that this definition has k squared there. But I'm clearly seeing on some web pages just k. In fact, Wolfram Alpha has just k, and I'm going to check Wikipedia. Hold on. Oh, it's interesting. Wolfram uses both definitions. It uses the k definition when it's talking about its software, and it uses the k squared definition when it's talking about the function in its mathematical library. For what it's worth, Wikipedia definitely uses k squared, so we're going to stick with k squared. For the Patreon viewers, in the book Why Does It Move, I go really deeply into all the notations for the elliptic integrals for what it's worth. I'm sure I've noticed before that there's variety in this parameter. You learn and forget things so many times, but regardless. The point is that this expression that allows us to convert from this metric, the metric expressed in the coordinates theta, to the metric expressed in the new coordinates theta prime, that derivative is easy to calculate, and it's easy to calculate if you remember the fundamental theorem of calculus, and that is it. Oops, I need a theta prime here. Remember, it's theta, the new function, as the old coordinates as a function of the new coordinates, right? So we're expecting this to be a function of theta prime. Seems backwards. It seems like if I'm swapping coordinate systems, I should have theta prime as a function of theta. But in the end, I would still need theta as a function of theta prime in order to do this derivative. If I was transforming a tensor, a contravariant tensor, I would need theta prime as a function of theta so I could do the derivative that way, right? So it is important to be able to invert these if you want to go back and forth and back and forth. I've actually chosen one. This is hard to invert. I don't know what the inversion is of the elliptic integral of the second kind. I think I know what it is for the first kind, but I don't know offhand what the inversion is for the. If you told me to transform a contravariant tensor, I couldn't do it because I don't think I can invert this. I'd have to work very hard to invert this so I could take the appropriate derivatives. But the way I've done it, I can do it, right? And notice how arbitrary this is. I just grabbed some crazy function out there and wrote it in a way so I know I could take its derivative, I guess. So I guess I planned it out that much. But you don't need, there's no restrictions on coordinate changes, right? That's the point. That's one of the things I'm trying to emphasize is you can dig into an infinity of different functions and make a coordinate change. Okay, so given that, I can now change the metric component, it's singular because it's a one-dimensional manifold, from the old coordinates to the new now because I can do this. And how would that look? Well, let's see. Well, the first thing is to write the obvious thing down. These two coming together give me this squared, so I just take the square root away, and now the new metric component is this factor times the old metric component. So what am I using for the old metric component? Well, you may remember you better remember, it's the whole point of the lecture, right? We had S1, we had phi, we had R2. R2 had the Euclidean metric, right, which was delta ij, or delta, well, yeah, it was delta ij. We had the Euclidean metric, delta ij, and we pulled it back, and we ended up with g theta theta equals r squared, right? That was the component. So there's only one, so this is with the circle embedding, right? The circle embedding. Oops, I forgot my factor of 2, right? I need a factor of 2 here, right? Because of this, right? In other words, this derivative here always has a factor of 2 in front of it. Let's see, if it always has a factor of 2 in front of it, that means I should have 1 from that, 1 from that. So I should have, this should be a 2 there, and then this should actually be a 4, right? And then this should be a 4. So that should end up with 4 minus 3 sine squared theta prime r squared, right? So 4 minus 3 sine squared theta prime, right? So this is my new my new metric, or it's the same metric, right? No, that's a very important point. It's not a new metric. It's the same metric. It's the same metric in a new coordinate system, right? So we're playing with coordinate systems. It's a new metric in the same coordinate system, and this coordinate system is this wacky thing that I chose. That was the elliptic integral of the second kind, expressed where the new coordinates, and I use scare quotes on new, are actually embedded in an expression of the old coordinates in terms of the new coordinates, right? Okay, so now I have this this expression down here. Let's have a look at that. So here is the expression that we developed for the component in the new coordinate system. And now I take this 4 and I blow it up this way. I say 4 cosine squared theta prime plus 4 sine squared theta prime, right? That's equivalent to 4, right? There's nothing different there. You pull out the 4, cosine squared and sine squared add up to 1, so that's not changing anything, and we leave that alone. But now I combine these two, and I end up with 4 cosine squared plus sine squared r squared. So this new version of the metric, remember, this metric was using phi is sine, what was it? Wasn't it sine theta, r sine theta, and r cosine theta, right? So this is the flat circular pullback, the pullback of the Euclidean metric using this circular transfer function, right? That's what this thing actually is. But the coordinate system has now been changed on the original metric Marshall. And so now the metric components look like this, which, if you remember right, was the other transfer function, modulo the fact that I think they took the derivative in the wrong order. So I guess their other transfer function was phi equals, I think it was this. I think it was ultimately this transfer function. But the point being that these different transfer functions are pulling back a metric in R2, and the difference in the pullback on those two transfer functions is suspicious because all I have to do is change the coordinate system, which is a very arbitrary function, which is a very arbitrary activity on the original manifold, and I can show that the pullback on this of the metric, of the R2 metric in the two circumstances is the same. And this is non-trivial, right? Obviously, I chose this thing, which I kept saying was totally arbitrary, wacky choice. It is an arbitrary and wacky choice. I have a million choices. I can do this a million different ways. I happen to pick the one that would exactly prove the point that the distinction between the pullback of the metric in R2 into S1 is a bit of a vacuous distinction because all I have to do is change the coordinate system, the way I label the points, and all of a sudden the distances are the same. And the answer is yeah, that's exactly all you got to do. So the question of whether two metrics are the same frequently comes down to the question of, can you find a coordinate system that simply transforms the pullbacks back into the same thing? Or I guess the way you should say it is, if I have two different metrics on S1, which is what I ostensibly have here, right? I have this metric with r squared, right, from this, and I had another metric. Or you could say it this way. I had this metric. Let's just say, forget the whole pullback idea. Just say you're looking at S1 and someone says, hey, here's a metric for you. And then somebody comes out around and says, no, I've got a metric for you. I've got, which is it? I've got this metric for you. All right, so you have this metric for S1, and then somebody says, oh, I've got this metric for S1. And you're saying, gee, I wonder, how dissimilar are these metrics, right? Well, if you can find a coordinate transformation that makes them the same or transforms one into the other, then there is no meaningful distinction. And that's what we did with this bizarre choice. Now, making this choice is actually really, really hard, right? You better know something about deep calculus you should know the beginning of deep calculus, right? I think math is so deep that it's hard to say that any element of it is deep because there's always like an infinite amount of deep in front of you. But, going beyond it, you better know more than just your elementary calculus to even understand this transformation, let alone find it, right? So that's a good exercise for the reader, right? Is figure out this transformation, if you like. You run this argument backwards. You end up with an integral, and that integral is this integral. And if you're on the ball, you recognize that this integral is an elliptic integral. Actually, you end up with, if you follow the paper, you end up with an integral that doesn't obviously look like an elliptic integral, but if you're familiar with elliptic integrals, you realize, oh, yeah, that's an elliptic integral. And then you transform it in this form, which is really essentially the reverse of this process, right? You end up with something that looks like this, under the integral sign, and then you invert it to get this, and then ultimately divide through by 4, and now you're in this territory, right? Anyway, the point is that it's hard to do in general. If you're just faced with sort of metrics that you've never seen before, and they're very complicated, this process of finding a coordinate change that will turn one into another is non-trivial, and sometimes it's not, well, usually it's not even doable. But the point is that some metrics hide their equivalent to each other based on this notion of coordinate equivalency. The two metrics we chose were pullback metrics from R2 to illustrate all of this. But so there's a couple illustrations we did. The first illustration we did is we talked about, we did another exercise of this process, the process of having a transfer function from one manifold to another, and then using that to pull back a cotangent field. We demonstrated that for S1 and R2 using the Euclidean metric on R2. We pulled it back into S1. We developed two different metrics on S1, both derived from different transfer functions. So now we have two metrics on S1. We demonstrated pullbacks and talked a little bit about manifolds. And then we went through this idea of a coordinate change on S1. And we showed that those two metrics on S1 were essentially the same modulo a coordinate system change, which is very uninteresting in the sense that the distinction between the two metrics is uninteresting because all you have to do is relabel the points and you've turned the metrics into each other. So we've kind of illustrated those 2 points. They're a bit independent. I could have started this whole thing with, hey, we have two different metrics on S1. And can we find a coordinate change that converts one metric into another? In other words, can we find a function theta of theta prime such that I can prove that this old metric, that I can show that this old metric equals the new metric, right? Just by these factors, can I do that? That's the other question. Oh, by the way, the 2 going here and here doesn't make any sense, right? D theta d phi prime includes the 2, right? It includes the 2. So let me get rid of those two 2's there. It does belong here, but these 2 include the 2, right? The derivative of this is you use the fundamental theorem on that, and then you have a factor of 2. So it includes the 2. So putting them there is not really correct. Okay, all right, so that's all for today. This is kind of a long lecture, but I really wanted to get at this very interesting part of this paper. And next, we should be getting into the Einstein tensor. Thanks.